next, I need to talk about the basics of caches. We need to understand caches, how caches actually are built. Then we will talk about cache performance, inshallah, and memory stall cycles in my next lecture. But we need to understand the basics of caches. So there are 4 basic questions. The first question that we need to actually answer, if we can answer these 4 questions, then we understand caches. The first question is that when we bring a block inside the cache, where do we place this block? So this is known as a block placement. And this would result in different ways to organize the cache. We can have the cache to be directly mapped, set associative, fully associative. I will talk about these in details. Second question, okay, how do you identify a block inside the cache? How do we know if a block is inside the cache or not? So we need some kind of a block identification. Okay, so when I would like to, I'm going to search the cache block by block. No, this is not really practical. So we need to actually identify blocks inside the cache, and we use actually some kind of, we have a block address, we have a tag, we have an index. So I need to talk about all of these in great details. The third question, okay, if we would like to bring a new block into the cache, we have to replace one of the existing blocks inside the cache because the cache has limited capacity. So therefore, when you bring in one block, you have to replace an existing block. So which block to replace? So that's called block replacement. So we can have first in, first out, or we can have random replacement, or the block which is least recently used. So these are different ways to replace blocks inside the cache. The fourth question is that what happens on a write? Now, in the case of the instruction cache, we never write. We just fetch instructions. So we only read from the instruction cache. But in the case of the data cache, we can read, we can write, because we have store instructions. And these store are going to write to the data cache. So we need the write strategy. So when we write to the data cache, do we write only to the data cache only? Or do we write to the data cache and also the lower level memory? That's also a question to be answered. So this is called the write strategy, specifically for store instructions. Let us take a look inside the cache. So here we have the processor. Here I have the main memory, and in between, I'm putting a cache. Of course, it's not really only one cache. We have actually multiple caches, but this is really the basic idea, okay? The basic idea. Now, the processor is going to send its address to the cache memory. As I said, we have like an instruction cache and data cache. Yani inside the CPU, not only we have one cache, we have at least 2 cache memories. We can also have a level 2 cache and even a level 3 cache. But let us just think about an address which is sent to any cache. So it does not really matter what cache we are dealing with. The processor is going to send an address to the cache. And the cache is going to respond with the instruction or the data. Okay? So if it was a data cache, then it's going to respond with the data. If it was an instruction cache, then it's going to send the other address. So it's going to send the instruction back to the processor. So whether you are so the cache is addressed the same way that you address the main memory. And the cache, you can fetch instructions or you can read or write data in the case of a data cache. Now, if the block is found inside the cache memory, then we can get the data very quickly. But if the block is not found inside the cache, then in this case, the cache memory is going to address the main memory. So it's going to send the address to the main memory. And the main memory is going to respond by sending a block of data from the main memory into the cache memory. Okay? So you see actually how this is happening. Now, inside the cache, we are storing the data, and also we are storing something else in addition to the data. This is what we need to understand. This is actually used for identification, to identify the blocks inside the cache. So now the cache consists of n blocks. So this is cache block 0, this is cache block 1. These are blocks of data that exist inside the cache memory, up to cache block n-1. So in total, we have n cache blocks. N is a parameter. Yani we can actually have a small cache, large cache, small n, large n. It does not really matter what is n. N, okay, it's just a parameter. Now, in addition to these, n cache blocks, we are storing tags. They are called tags. Now, tags is a part of the memory address. Now, remember that n here, the number n of cache blocks, it's much smaller than the number of blocks that exist in the main memory. Main memory is much, much larger than the cache memory. So cache can only store a subset of the blocks that exist in the main memory. So for this reason, we need to identify which blocks exist inside the cache memory. So for this reason, we use tags. So tags are used to identify the blocks inside the cache memory. So each block will have a tag. So the first block will have tag 0. The second block will have tag 1. And the last block will have tag n-1. So we have two arrays. We have an array of blocks and we have an array of tags. Okay. So what is a tag? A tag is part of the memory address and it is used for block identification. I will show more details about the tag in the next few slides. Right? So it's called a cache block or a cache line. Okay, some people call it a cache line, but it's the same meaning. And it is the unit of data transfer. It's the unit of data transfer between the main memory and the cache. And if a block is not found inside the cache is going to transfer a block, not one byte, not one instruction, not one data item, a block. And today, in recent caches, people use large blocks, 64 bytes of data. So the block size here is 64 bytes of data. So the cache is going to request 64 bytes of data to be transferred from the main memory into the cache. Okay. This is inside the cache memory. Okay, so we have two arrays, an array of blocks, and each block is typically 64 bytes of data. And we have a second array of tags. And tags are identify the blocks inside the cache for block identification. Now, yes, Tfaddal Ali.
In the first case, Doctor, how we can fill the cache memory?
We fill the cache memory. The cache, okay, has a special logic controller inside the cache memory. It's a sequential circuit inside the cache memory that if we have a cache miss, then the cache actually is going to request the block from the main memory. So this is done automatically by the hardware. So there is a cache controller which is part of the cache memory, which is responsible of requesting blocks from the main memory and filling the blocks inside the cache. So the cache does it automatically and transparently. So the programmer does not really do this. It's the hardware, the cache, which is doing it. Okay, Ali, does this answer your question?
Yes, but I mean, in the first condition, I mean, the processor.
Initially, the cache is empty.
Yeah, initially.
The cache is initially empty. So as the program will start generating memory addresses, the cache will find that the blocks is not really inside the cache. So the cache will start requesting these blocks to be transferred from the main memory into the cache memory. And then in the future, when the program starts finding these blocks inside the cache, then it's going to start to hit inside the cache, and the program will start running at a higher performance, at the higher speed.
Okay, good.
Now, block placement. How do we place the blocks inside the cache? So I said that we have 4 questions that I need to actually answer. The first question is about the block placement. Now, the cache can be directly mapped, or it could be a fully associative or set associative. So let me talk about these are different ways to organize the cache. So remember that here the block is the unit of data transfer between the cache and the memory. Right. So here I'm showing a small cache that has only 8 blocks that are indexed from 0 to 7. I'm showing here the index in binary, starting here from 000 to 111. Okay, so only 8 blocks indexed from 0 to 7 in binary. And here I'm showing main memory, which consists of 32 blocks. Of course, the main memory is much larger than this, but this is for the purpose of illustration, to illustrate the meaning of direct or block placement, directly mapped cache. So, so here we have, let us say, 32 blocks, which are also have block addresses in binary. Okay, now each block can consist of 64 bytes. It does not really matter, but we are looking at the main memory as blocks and the cache as blocks. Okay, So to do the direct mapping between the main memory and the cache, we use, for example, the least significant 3 bits of the block address to index the cache. So notice that here, for example, these are the least significant 3 bits I'm highlighting. So notice that this green block here ends with 001. Let me use here my pen tool. So notice that this is 001 here. Okay, so therefore we map it to the block at index 001. This is called direct mapping. Okay, the same block here, which is shown in green, ends with 001. The least significant 3 bits are 001. This block also ends with 001 again. So you can have many blocks inside the main memory that end with 001. So all of them are mapped to the same cache index that ends with 001. That's called directly mapped cache. Okay. Of course, the cache has to have extra information. The tags. The tags will indicate, okay, which block in memory which is stored inside the cache. But if there is a cache miss, then basically you send the block address to the main memory, and the main memory is going to transfer the block, and the block will be mapped, and it will be stored at a specific index inside the cache. So we extract the cache index. So the cache index will be the least significant 3 bits of the block address. This is just an example, which is called directly mapped cache. Now, how do we implement this? Okay, in the hardware. So now the address itself is divided into 3 parts. Okay, so we have the block address, and the block address, let me just go back here to, okay, yeah. So this is here my, where is my pen tool? Yeah. So this is my block address. Now the complete address, for example, can be 32 bits. Okay, so for example, in the MIPS architecture, 32-bit architecture, the addressees are 32-bit addressees. This is how we address the main memory. Now the address, which consists of 32 bits, it is divided to 3 parts. Okay, we have an offset. This is called the block offset. Now, why do we have an offset? Okay, let me add, because of limited time. Okay, let me answer this directly. Now, the block offset is important because the block is not just 1 byte or 1 word. No, it consists of 64 bytes. So we need to specify inside the block, we need to specify the offset. So the offset is used inside the block because the blocks can be large in size. So for example, if you have the block size, which is 64 bytes, I need 6 bits here for the block offset. So let me just write here 6. This will be the number of bits here for the block offset. This indicates that we have 2 to the power 6, 64 bytes inside the block. Yeah, for example, if you would like to load 1 byte, okay, you need to specify what's the offset inside the block. That's the importance of the offset. The upper part of the address is what we call the block address. So this is how we identify the block inside the main memory. But this is divided into 2 parts. We have an index and we have a tag. Now the index actually is used as a cache index. So the cache is indexed, and the index here will specify what is the index of the block inside the cache. So for example, if we have, let us say, I'm going just to throw a number. Suppose that we only have 8 blocks inside the cache, only 8, as we have seen in the previous slide. Then if we have only 8 blocks inside the cache, we only need 3 bits for the index. So we can index it from 000 to 111. So from 0 to 7, so we only need 3 bits for the index if we have only 8 blocks inside the cache. If we have, let us say, 1024 blocks inside the cache, then we need 10 bits for the index. Okay, that's the meaning of the index. Now, the rest of the block address, or the upper bits of the block address, are what we call the tag. Now, the tag is very important, and we use it for block identification. Okay, we use it for block identification. So first, we index the cache. How do I know that the block is found inside the cache or not? If this cache is directly mapped, we use the index to index the cache, and we go to only to one block. So the block must be at a specific index. And therefore, we look at the tag inside at this specific index. If the tag in the address matches the tag which is stored inside the cache, remember that the cache itself is divided into a data array and a tag array. I'm showing all of them here. So here I'm showing the data is shown in blue and the tag is shown in green. So these are a few bits, the upper bits of the block address. So we compare the tag. We use a comparator here. You can see there is a comparator. And this comparator is going to compare the upper bits of the block address against the tag which is stored inside the cache. So if these match, also we have a valid bit. So this B here indicates that this tag is valid because initially you might clear all the valid bits to indicate that the cache is empty. So if the tag in the address matches the tag which is stored inside the cache, and the block is valid, the valid bit is set, so we have an AND gate, then we say that we have a cache hit. And we can actually get the data directly from the block inside the cache at a specific offset. Okay, so that's how we read, okay, data from the cache. We can write exactly the same way, but we stored it. So if we have a hit, we can also store. We can write to the cache. So this is the meaning of a directly mapped cache. That's how it is organized. Please interrupt me if you have any question.
So, Doctor, the offset would be able to access
the different bytes inside the block. Inside the block. Okay. So the offset is only for data. Inside the block. Yes.
Okay.
Because the block itself can be 64 bytes. So I would like to load 1 byte or 2 bytes or 4 bytes. So I need to specify the offset.
Okay.
Okay. This is the importance of the offset.
Doctor, what does hit mean? What does it do?
What does it do? What?
Hit.
Hit actually is very important, okay, for the CPU. So if there is a hit, it means that the block is found inside the cache. If there is a miss, it means that the block is not found inside the cache. That's the importance of this hit signal. So this hit signal indicates to the CPU that you can actually have the data continue at maximum speed. Okay, there is no need to stall the pipeline. However, if we don't have a hit, we say we have a miss. And if we have a miss, it means that the block is not really found inside the cache. Okay, it could be a block of instructions or a block of data. It does not really matter. It's the same organization. Whether you are designing an instruction cache or a data cache, it's exactly the same way that we are organizing it. So if we have a miss, it means that we are telling the CPU, wait. Okay, we cannot really fetch the instruction, or we cannot really load the data. Then wait, store the CPU until we transfer the block from the main memory into the cache. Okay, Khalid?
Yes, Doctor.
That's the importance of this signal. So this is actually used to control, okay, the CPU. I need to continue. Okay, so this is the meaning of the cache hit. Okay, so it indicates that the block is stored inside the cache. Now notice that here we have a relationship between the offset, the index, the tag, and also the size of the cache, the capacity of the cache. Now, if we say that we have here n bits for the index, so let me write here a small n. Okay, this is not n. I'm sorry. I'm writing with a with a mouse. That's really difficult to do. So here we have n bits. This is actually for this field here, for the index. Again, let me try one more time. This is my pen tool. What is my actually pen? I'm just trying to locate my pen. For some reason, I cannot really find it. Just 1 second. Give me 1 second. Anyways, let me just do one more time because I'm running out of time. So let me put here n on top of that. So this is here n. Okay, that's n. Okay, so we have n bits, okay, for the index field. So if you have n bits for the index field, then you can have 2 to the power n indices. So you can actually index 2 to the power n blocks inside the cache. So the number of cache blocks will be 2 to the power n. So n here is the number of bits in the cache index. If you have b here for the block offset, so let me write here small b. Not bad, okay, I can write actually with the mouse. Then if this is actually b, which is used actually for the number of bits in the offset, then you can have a block which consists of 2 to the power b bytes. So the block will be 2 to the power b. This is the number of bytes inside the block. Okay. So for example, if you have the b equal to 6, then the block size will be 2 to the power 6, which is 64 bytes. Okay. So that's the importance of the offset. Now you can say, okay, what's the capacity? Before that, okay, if you have 32 bits in total, okay, for the block, for the address, then the tag will be 32 bits minus n minus b. That will be the number of bits for the tag. And we say that the cache capacity or the cache size, that's actually how much data you can store. You will have 2 to the power n blocks, and each block consists of 2 to the power b bytes. So it's 2 to the power n plus b bytes. That will be now the cache capacity, the cache size. Okay. So that's a directly mapped cache. Now that's one way to design a cache. It's not really, it's the simplest way, in fact, to design and implement a cache. But it's not really flexible. There is a more flexible organization for a cache, which is called associative or set associative. I need to talk about these next time, but I'm running out of time. So I might need actually 2 extra lectures, actually, in fact, to finish this topic, because I need to talk about more about cache organization. I need to talk about more topics are related actually to how do we deal, okay, with writes and how do we deal with replacement of blocks inside the cache. So there are more topics to this, okay? So cache is actually a big topic, so I need to talk more about more details. And then I'll talk about also the performance of the cache. Okay, so what happens in the case of a cache miss? We lose cycles. So what will happen to the performance? So this is also something which is very important. So I need 2 extra lectures, okay, to finish the topic about caches and cache performance. So in the case of directly mapped cache, the address itself, the address is divided into different fields from the cache point of view. So it's just one memory address, but we are breaking it down into 3 different fields. So the least significant bits here, which is called the offset, indicates the offset within a cache block. So the unit of data transfer between the main memory and the cache is the cache block. Okay, so the cache block, for example, can consist of 64 bytes. And if it consists of 64 bytes and you would like just to load 1 byte, then you have to specify the offset. So the offset here, for example, for 64 bytes, the offset will be 6 bits. So in general, I talked about this last time. So in general, if we have here, if we have B is the number of bits for the offset, then the number of bytes within a block will be 2 to the power B. That will be the block size. If the cache is indexed, because it's directly mapped, it is indexed. And the number of bits inside the index depends, of course, on how many blocks you have inside the cache. So if you have, for example, the number of cache blocks is 2 to the power n, that's the number of blocks inside the cache, then you need n bits, okay, for the index. So the index will take you to only 1 block inside the cache. So the cache is mapped, okay, so the block is mapped to a specific index. So the index is extracted from the address and we map the block to that specific index. And then at this specific index, we store a tag. So notice that not only we are storing the data, but also we are storing the tag inside the cache. Now the tag here will be the upper bits of the address. Okay, so it will consist, if the total address is 32 bits, then we say 32 minus n minus b. This will be the number of bits which are used for the tag. So this is how many bits we need, okay, to store the tag inside the cache. So the cache is not only storing the data, but also storing the tags, and the tags are used for block identification. So every time we present an address to the cache, we have to look up the cache. And therefore, if the tag in the address matches, it's identical to the tag which is stored at this specific index. So we use a comparator here to compare the tag in the address against the tag which is stored at that specific index inside the cache. If these two tags are equal and the entry is valid, so we are using here a V. V means valid bit. Okay, so for each entry inside the cache, for each cache block, we indicate if it's valid or not. So if the tag matches the tag and it is valid, so we are using an AND gate here, then we say that we have a cache hit. Otherwise, we have a cache miss. It means that the block is not found inside the cache. Notice that we are not really comparing the tag against all the tags inside the cache. We are comparing it only with one tag at that specific index. Now, the cache size or the cache capacity is how much data you can store inside the cache. So you count the number of blocks, which is 2 to the power n is the number of blocks, multiplied by the size of each block, which is 2 to the power b bytes. So 2 to the power n multiplied by 2 to the power b is 2 to the power n plus b bytes. That's how much you can store as data. This is the cache data size or the cache capacity. Now notice that the tags are also stored, but it's not really considered to be data. This is an overhead. Okay, so we are storing extra bits inside. So in addition to our data array, there is a tag array, and the tag array is used for block identification, and it is considered to be an overhead. Okay, because we have to store them. Okay, anyways. Okay, to identify the blocks inside the cache. So we don't really count it as part of the cache data size, but we can also count how many bits we are storing inside the cache for the tags and for the valid bits. So this is all overhead, which is needed to implement the cache. Okay. I have a question. I have an example about the directly mapped cache. Here's an example. Okay, so suppose that we have a directly mapped cache that has 256 blocks, and each block is 16 bytes. That's the block size. And suppose I present a 32-bit address. I'm showing here the address in hexadecimal. So this is my address. So how do I extract, okay, the tag, the index, and the offset, the byte offset from this address? This is my question to you. How do you do this? How do you compute the tag, the index, and the byte offset from this address? Students?
Yeah, yes, Doctor. We know that 256 is 2 to the power 8. Then n equal to 8.
Yes.
And for the block size, for the number of bytes in the offset, 2 to the power 4.
Yes.
Then we know it's b equal to 4.
Yes.
We found the index and the byte offset, and the tag is equal
32 bits, because 32. This is, notice that this is a 32-bit address.
Yes, 32 bits.
Yeah, so no, the entire address is 32 bits, but the tag will be 32 minus the 8 bits for the index minus the 4 bits for the offset. So we subtract 32 minus 12, we get 20 bits, okay, for the tag. So if I would like to draw now my 32-bit address, now notice that this address consists of 32 bits. I'm showing it in hexadecimal, but we know that in hexadecimal, each digit is 4 bits, right? So therefore, we have here 8 digits. These are 32 bits, but it will be a lot more convenient to show the address in hexadecimal than 32 bits in binary. But you can, of course, convert it to binary. So the offset will be 4 bits because we have 16 bytes is the block size. The index is 8 bits because we have 256 blocks, as Amr mentioned. And of course, the upper 20 bits, these are the remaining bits. These are used for the tag. By knowing that, can you extract? Can you tell me what's from the address? Can you tell me what is the offset, the index, and the tag? I need someone else other than Amr to answer this question.
Yes,
I need to know what is the offset. Yes, Khalid.
C.
Yes, it's in hexadecimal, of course. Yes.
Yeah.
What is the index?
It is 8A.
صحيح. And
the remaining is the tag.
Yes. Okay. Thank you very much. So that's basically it. That's the byte offset, which is C in hexadecimal, which is 12 in decimal. That's the offset. So if you are, for example, loading a specific byte at this address, then it will be this offset. And the cache index is 8A in hexadecimal. If you convert it to decimal, it will be 138. And the upper 20 bits, these are the upper 20 bits. This is the tag. Okay. So you understand this topic. It's very important to understand what's the meaning of a tag, index, and what is the offset, okay, inside the block. Now here is a second example. Okay, here's a second example. We're looking at a small directly mapped cache with 32 blocks. So when I say 32 blocks, what does it mean? 32 blocks. How many bits do I need for the index? This is actually the click in your mind. Well, when I say 32 blocks, something has to click, which is the index, right? So the index, how many bits do I need for the index?
5.
5 bits, yes, 5 bits, yeah, sure. And we have the cache is initially empty. It says it's initially empty. So we're going to start with an empty cache. For example, all the valid bits can be zeros, okay, indicating that it is empty. And the block size is 16 bytes. So when I say the block size is 16 bytes, what does it mean? Automatically, the offset comes to my mind. That's actually how it should click. So how many bits for the offset? We have seen it in the previous example. 4. 4, yes, 4 bits. Thank you. Now, notice that these memory addresses are given in decimal. What shall I do? It says that we have here a sequence of 6 addresses. It says that map these addresses. Now, when I would like to map these addresses, what shall I do? Yes, somebody was saying something. Yes, Ali,
yeah. Shouldn't we convert it to hexadecimal first?
Exactly. Convert them to hexadecimal or to binary. Either way is fine. Okay. Why do we need to convert them to hexadecimal or binary?
That we can map it to the memory.
We need to extract the index. What's the meaning of mapping?
Yeah, to extract and as you said,
find the index. Because when you map it to a specific index inside the cache. That's the meaning of mapping. Yes. And indicate whether you have a hit or a miss. That's also which is needed in this example. Now, this is the solution. So we have 4 bits for the offset, 5 bits for the index, and the upper 23 bits for the tag. Now, we look at each address. We convert it from decimal to hexadecimal. Now, notice that the cache index consists of 5 bits. Now, notice that 8 here is the offset because it consists of 4 bits. Now, if it consists of 6 bits, if we have like a 64-byte block, then you need 2 extra bits. Okay, and then you have to take them from the E. But in this example, it was simple. It was only 16 bytes, 4 bits for the offset. So automatically, we can say that it is 8. Now, for the index, we have 5 bits for the index. So the E is not enough. I need 1 extra bit. So this extra bit has to come from the 3. It will be the least significant. So you can convert it to binary, and then you can extract 5 bits. So basically, we have the E, which is 4 bits. And this one here, so I say 1E, so this one here comes from the least significant bit of the 3, because 3 is actually what? 0011 in binary. When you convert it from hexadecimal to binary, you get 4 bits, 0011. Now notice that all the upper bits are zeros. I'm not really showing them, but you can actually just put them as zeros. So 1E here is my cache index. So this is how I'm mapping it. I'm extracting the index from the address. So this will be the cache index. So we go to this index. Now, initially, the cache is empty. So all the blocks are invalid. So the valid bit equal to 0. So that's a miss. So every time we start with an empty cache, we start by having cache misses. And then as we start filling the cache with the blocks, then maybe later references to the cache, when we address the cache, then there will be cache hits. So that's a cache miss. That's because it's a first access and the cache was initially empty. Now, the next address is 1004. I can convert it also to hexadecimal. Notice that the offset is C, but the index is the same. It's also 1E. Now, that must be a hit. Why? Because already we got a cache miss and we transferred the block from the main memory into the cache. So we have the block inside the cache. And now next time when we address, okay, when we index the same block inside the cache, it is valid. And therefore we have the block and therefore it is a hit. Okay. If we continue, now notice that the next one is 1008. If you convert it to hexadecimal, you get 3F0. Now, if you would like to extract the cache index, it must be the 1F. That's the index. Now, that's a different index. Okay, a different index. Initially, it's invalid. The block is not really found there. So we got a miss. So we get a miss. Okay, clearly we get a miss. Next one. Now notice that here I have a different address here, and so this is 9F4. Now if you extract the cache index, 9 is 1001 in binary, so it ends with a 1, and then you take the F, you get actually the same cache index 1F. But is it a hit or a miss? It says clearly that it is a miss. Why?
Says a different tag because
yes.
the tag will be different.
Yes, if you look at the upper bits here, they are different. So basically the 3 here ends with, so it's actually, so when you extract the tag from the 3, it ends with a 1. So basically it's all zeros and there is a 1 at the end. Whereas here in the case of the 9, you have actually, it ends, once you take the 1 away, it will end with 100. It was 1001, but we took the 1 with the F, and therefore it ends with 100. So the tag is different. If you look at the tag, so it's not enough to look at the cache index, you have to look also at the tag. So the tag does not really match the tag. The tag is the tag for the previous block. Okay, so it's a different address, different tag, and even though it maps to the same cache index. So therefore, what will happen is that we get a miss and we transfer a block from a different block, from the main memory, but at the same cache index. So basically, there is some kind of a replacement, cache replacement inside the cache. So one block is going to replace another block at the same index. So these are 2 different blocks in main memory at different addresses in the main memory, but they map to the same index. Okay. So that's, you need to understand this. Now, if you continue like this, okay, the next address here is 9F8. Now notice that the offset is different, but it's exactly the same index and it's exactly the same tag. So we have a hit. And we continue like this. Again, it's the same index, the same tag, the same index. So again, it is a hit. So this is basically how you can determine, okay, from a sequence of addresses, whether you have hits or misses. In fact, there is a small simulator inside the Mars tool about caches. And then you can actually take a real program that generates real addresses. And then it will tell you if you have a hit, it will count how many hits and how many misses. This is very important from the performance point of view. I'll talk about performance. I'll come back to it. So what we have seen in the previous slide was a directly mapped cache. We have a different type. Yes, Khalid, tfaddal.
Yes, Doctor. I didn't understand how we extracted the index and what's the relation between the tag and index and the hit.
These are two different things. The index is used to index the cache. The tag, we are storing it inside the cache. I'm not showing the cache here, but we are storing the tag inside the cache. So notice that the tag here for these three addresses is the same thing. Notice that how it's actually the same. Just look at it in binary. It's the same tag. It's the same index. So basically, it's the same block, okay, in the main memory that we are transferring it. So here we have the same index, but a different tag. So these are two different blocks in memory, but they map to the same index inside the cache. So when you have the tag that's different from the tag, we say that we have a cache miss. It's not a cache hit. Okay. So these are two different blocks inside the main memory that are mapped to the same index inside the cache. But the cache knows that it's a different block because the tag is different. So the tag which is stored inside the cache is different from the tag which is in the address itself. Okay.
Okay.
So now we look here into a fully associative cache. Now, a fully associative cache is a different organization of a cache. Now, the problem with directly mapped cache is that you have to map it to a specific index. And here we had two blocks in the previous example. We had two blocks. Okay, for example, at different addresses. Here we can see that we have 3F0 and 9F4. Okay, these are two different blocks in memory, by the way, at two different addresses because they have different tags. So these are two different blocks, but they map to the same cache index, which is 1F. And because they map, one is going to replace the other. Right? What if I would like to have both of them in the same cache at the same time? Now, that's not really possible in the case of directly mapped cache. So directly mapped, although it's very simple, the problem is that you can actually get conflicts because you have different blocks that are mapped to the same cache index, and they start replacing each other, even though the program might need them at the same time. The fully associative cache is much more flexible because it allows you to have these different blocks at the same time inside the cache. So you can place the block anywhere inside the cache. So there is no indexing. So in the case of fully associative cache, there is no index. So what do we have? The address is divided into two parts. We have the offset and we have the tag, and that's it. There is no index. So when you bring a block inside the cache, you can place it anywhere inside the cache. So for example, here, I have a small cache, which is fully associative. It consists of 4 blocks. Okay, notice that there is no index. And when you bring a block, okay, you only store the tag inside the cache. Now, if you are going to place blocks anywhere inside the cache, so you have to compare, and you would like to present a new address into the cache, you have to compare the tag in the address against all the tags that are stored, that are associated with all the blocks inside the cache. So each block inside the cache will have its corresponding tag. And therefore, what we have to do is that we have to compare this tag, which is part of the address, against all the tags that are stored inside the cache. So each block will have its own tag, and we compare. So we need actually here multiple comparators. So if you have M is the number of blocks, then I need M comparators. Okay, so that's if you have M blocks. So each block will have its tag and its comparator. So we're going to increase the number of comparators. In the case of directly mapped cache, we only use one comparator, regardless of how many blocks. I can have thousands of blocks inside the cache, no problem. You only need actually one comparator because you index first, you go to one block inside the cache, and then you compare. Here, what we are doing is that we are comparing in parallel, okay, the tag against all the tags. That's a different way to organize the cache, to implement the cache. And then after that, we check, of course, the valid bit. Now, one of them is a hit, okay, at most one of them. You can actually have all of them missing if the tag does not really match anyone. But at most one of them is going to be a hit. If there is a hit, we use an OR gate if there is a hit, then we know that actually that we need to find out that which one is a hit. So we can use a multiplexer to select our data from one of these blocks. So we get the data, okay, from one of these blocks. So we need an extra multiplexer. So this is going to increase the cost of the fully associative cache. And because we are using many comparators, so the number of comparators is equal to the number of cache blocks. And we need a large multiplexer. Its size is going to increase according to how many blocks we have inside the cache. So if you have at least one, if there's a hit, okay, then we have to know that which one is a hit. So we have to select our data. This is the purpose of the multiplexer. Now we call it M-way associative. That's the meaning here of an associative cache. Okay, so it's called M-way because we have M blocks and we have M comparators. So this is why it's called an M-way. And the cache data size, we are storing M blocks inside the cache, and each block is 2 to the power b bytes. That actually is the cache size. In this example, M is equal to 4, so that's a 4-way associative cache. Now, the problem with the fully associative cache that we have seen in this slide is that the cost of the cache. If you want to increase the size of the cache, you want to have thousands of blocks inside the cache, then the cost is going to increase because you are going to add a comparator for each block. And also the size of this multiplexer is going to become larger and larger. And this is going to make it even slower because you have actually to select your data. So as you increase the size of this multiplexer, then it becomes slower to access. So the cost becomes a problem and the cache becomes slower. So for this reason, people don't use fully associative caches, okay, because they are expensive and they are slow. Okay. Now, the alternative is to have something which is not fully associative, but there is some kind of associativity inside the cache. So it's called set associative. So the meaning of a set, it's a group of blocks that can be indexed. So we bring back the index, but we would like to have sets inside the cache. So the way it's organized is as shown here in this slide. So this slide explains, okay, the organization, shows the organization of a set associative cache. So we can have a set here consisting of 4 blocks only. You can have only 2 blocks or 4 blocks within the set. And here the set is shown as a row in this diagram. So you have here, for example, 4 blocks within a set. So the address now, this is the memory address. It's divided into, again, we still have the offset as before. Nothing has changed about the offset because this depends on the block size. But now we are bringing the index, okay, as we had it in the case of directly mapped. But the difference here is that when we index, we don't index one block. We index a set. And the set can consist of M blocks. M here is equal to 4. So we call it M-way set associative cache because we have M blocks within one set. So that's the meaning of M-way. We have 4 blocks. We have M blocks in general. In this example, in this slide, I'm showing 4 blocks inside the set. Now, you can actually have thousands of sets, but there are only 4 blocks within each set in this example. And therefore, the number of comparators is actually small. Okay, it's only equal to 4 as shown in this slide because M is equal to 4. So we call this a 4-way set associative cache because M is equal to 4. And you only need actually 4 comparators. So first you index, like we did in the case of the directly mapped cache. So first we index. And then after indexing, we go to only one set. And within this set, we compare the tags against the tag in the address. So if we have only 4 blocks within a set, then we need actually only 4 comparators. And then notice that if any one of them is a hit, we say that we have a hit. If all of them are misses, then we say that we have a miss. If we have a hit, then we need a multiplexer, and the multiplexer will be small because we only have 4 blocks, okay, within the set. So this will give us some flexibility. So the multiplexer here will have only 4 data inputs, and we use here the output of these AND gates actually to select the data, and then we get the data at the output of the multiplexer. Okay. So this will reduce the cost of the set associative cache, while at the same time it provides flexibility, because we have the flexibility to place the block, okay, within the set. So first we have to index, but we have 4 blocks, so we can choose, okay, where we would like to place the block inside the set at that specific index. So the index is still there, so we map the block to a specific index, but we have the flexibility within the set to place the block. Okay. Now, if you would like to look here at the parameters, okay, that we use for this cache. So first we look here at okay, the number of sets. So if you use n bits here to index, we call it the set index. If this set index consists of n bits, notice that we are extracting this from the address itself. Okay, so as shown here, that this index here will consist of n bits. And if I would like to write here, let me use my pen tool. I'm going to write n on top of this index. I'm going to write b on top of this offset, like we did in the case of the directly mapped cache. So if we have n is the number of bits here for the set index, then we have 2 to the power n. This will be the number of sets. Okay. Now, if within each set we have m blocks, in the slide we showed 4 blocks. You can actually have, if you have only m equal to 1, it will be directly mapped. But if you have m equal to 2 or 4, then it will be a 2-way or 4-way set associative cache. In general, if we have m blocks, we call it m-way set associative cache. And we need here to compare, to check m tags within one set. Okay, so we go to one set, we index the set, and then we can compare their tags in parallel using m comparators. So here m will be small. Okay, 2-way, 4-way, that's it. Sometimes we go to 8-way set associative cache, but not really very large m. Okay, so you can have thousands of sets, but within each set you only have a small number of blocks. Then the cache data size, we have 2 to the power n sets. We have 2 to the power b bytes per block. That's actually is b, the number of bytes per block. And we have m is the number of blocks inside each set. So if I would like to count the number of blocks, it is m multiplied by 2 to the power n. And each block consists of 2 to the power b bytes, so we multiply it by 2 to the power b. And this will give me the cache data size. That's the capacity, how much data you can store inside the cache. Now, if you look at these parameters, if you make m is equal to 1, if you make m is equal to 1, then it becomes directly mapped because there is only one block at in each set. So when you index, you only have the index of one block. But here you can have m equal to 2 or m equal to 4. So that will make it set associative. Okay, so you can actually have multiple blocks inside the set. So the meaning of directly mapped, directly mapped is like set associative, but m is equal to 1. That's it. And if you have it as fully associative cache, okay, then it means that there is only one set. There is no index. Okay, so basically there is no index, and therefore we have here n equal to 0. So 2 to the power 0 is equal to 1. You only have one set. Okay, that will make it actually fully associative. So you can think about set associative is in between, okay, two extremes, directly mapped and fully associative, and the set associative is actually the preferable configuration. So it provides more flexibility, okay, than the directly mapped cache, while at the same time we are reducing the cost. Okay, so we don't want to make it very costly in terms of the number of comparators, and we reduce the number of comparators, we reduce the multiplexer, okay, to select the data. طيب. Any question about this set associative cache? So now we understand the meaning of set associative caches. I need to talk also about the write policy. Okay, we still actually have few issues that I need to talk about to understand fully caches. The write policy indicates what happens when we write to the cache. So when we have a data cache, we can read, we can write. Reading is not a problem. You can actually get a cache miss. You transfer the block from the main memory into the cache, and then future reads will hit in. So reading is not a problem. The problem is with writing. Now, when we would like to write to the cache, what is the policy? Now, we can have write through or we can have write back. Now, the meaning of write through, okay, it means that we update the cache, but also we update the lower level memory. So the write will go through. So we are writing to the cache, but also we are writing to the memory. So every time we write to the cache, we have to write to the memory. That's the meaning of write through. So we only need actually a valid bit that indicates that the block is valid, okay, inside the cache. This is only it's needed. This is my cache control bit that indicates if the block is valid or not. And memory has the latest data, because if every time I write to the memory, then memory is, and the block inside the cache and the block inside the main memory are identical, because we are writing to the main memory every time we write to the cache. Now, if I would like to replace the block inside the cache, we can simply discard it. Why? Because we already have the block in the main memory. Fine. That's actually is called write through. Now, the problem with write through is that it requires a lot of memory bandwidth, because every time I write to the cache, I'm writing to the main memory. That actually requires a lot of bandwidth. And for this reason, okay, people don't use write through, okay, unless we have a second level cache and we can write to the second level cache rather than the main memory. But it requires a lot of bandwidth. That's the problem of write through. Now, people prefer to use write back. Now, write back policy is reduces the memory bandwidth. Okay, so the meaning of write back is that we use 2 bits inside the cache. We have a valid bit as before, but now we introduce a modified bit. Now we write to the cache, but without writing to the main memory. But we indicate that the block is modified inside the cache. That's the meaning of the modified bit. So when we write, we set the modified bit. We indicate that the block is modified. So now the block which is in the cache is different from the block which is in the main memory, because it has been modified inside the cache. But the block in the main memory is still the old block. It has not been modified yet. So we are writing to the cache, but without writing to the main memory. So we have 2 different blocks, but we have indicated that the block inside the cache is modified using this modified bit. We just need 1 bit per block, and then we set it to 1 if the block is modified. Now, the interesting thing about write back is that you can have multiple writes. You can write different bytes inside the block. So modified, 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 you can modify it 10 times, 100 times. It does not really matter. We just need actually 1 modified bit, just 1 bit to indicate that the block has been modified without writing anything to the main memory. So therefore, we are reducing the bandwidth. We are not really every time we want to write, we would like to access the main memory. No, there is no need to access the main memory. So for this reason, we say that we are using less memory bandwidth. Okay, that's the beauty or the advantage of write back. However, it's more complex to implement than write through. Now, why it's more complex to implement? Because at the time of replacement, when I would like to replace the block, would like to take it out from the cache, we have to check the modified bit. If the block has been modified, then at that time, we write it back to the main memory. This is why it's called write back. So only at the time of replacement, we have to check. If the block has been modified, write it back. If the block has not been modified, there is no need to write it back. You can discard it. It's still clean, okay? It was not. So this is the importance of the modified bit. So we delay the writing, okay, writing to the main memory until the time when we would like to replace the block. Okay, is this clear?
Yes.
So now what happens on a cache miss? Every time we have a cache miss, we have a miss signal. Remember the hit signal? So if this hit signal is actually 0, that's the meaning of a miss. So that's the miss signal. Okay, so the hit signal can be used as a hit or a miss. So in the case of a cache miss, this is a problem. Okay, we have to stall the processor. Okay, this is important because this is actually something that we're going to refer back to it when I talk about the cache performance. Now, the cache has to decide which cache block to allocate or to replace, because now we are going to transfer a block, okay, from the main memory into the cache, and therefore we have to allocate a new block. And if all the blocks have been allocated, okay, we have to replace. So that's actually is that what the cache has to decide. Okay, if there's only the cache is directly mapped, there's only one choice. So for directly mapped caches, we know which block to allocate or to replace. It has to be at this specific index. However, if you have a set associative cache, you can have multiple blocks I'm sorry, inside this set, and therefore we have multiple choices. Okay, we have multiple choices. Okay, if you have a set associative cache or a fully associative cache, so we have to decide that which block to replace. Okay, and therefore this is the replacement algorithm. Now we have to transfer the block from the lower level memory to this cache. Okay, so when I say here the lower level memory, it can be the main memory, or if you have a cache hierarchy, we can go to the second level cache and transfer the block to the first level cache. But forget about here the level 2 cache. We go all the way to the main memory. If the block is not to be found in any cache, we have to go all the way to the main memory and transfer it into the cache. And once we have transferred the block into the cache, we have to set the valid bit to indicate that the block is valid. We have to change the tag. We have to specify the tag, okay, for this block that has been transferred from the memory into the cache. So the tag field is now stored inside the cache, okay? Now, here is the interesting thing. If we are using the write back policy and I'm going to replace a block which is in the modified state, then we have to write it back. So not only we have to transfer a block, we have to check the block which is replaced inside the cache. If this block has been modified, so we wrote to this block, then what we have to do is that before it is replaced, we have to make sure that this block is written back into the main memory. Okay, that's actually if the block has been modified. Otherwise, if the block has not been modified, there is no need to write it back. You can just simply discard it and replace it with another block. Now the instruction is waiting. So this instruction has to be restarted. The instruction that wants to access the cache, okay, that caused the cache miss, it has to be restarted. And therefore we have a miss penalty. And this miss penalty is very important because I'm going to use it in the case of the cache performance. It takes, okay, cycles, okay, to transfer the block from the main memory into the cache. So the meaning of the miss penalty is how many clock cycles it takes to process. So miss penalty means time or means clock cycles. Okay, so how many clock cycles it takes to process a single cache miss? Of course, the hardware is taking care of all of this. The cache controller is taking care of all of this. And therefore, once it has transferred the block, so there is actually a certain time which is wasted here. Okay, so that's the miss penalty. So there's a penalty for each cache miss, and the CPU is waiting, okay, for the block. And therefore, we're going to store the CPU according to this miss penalty. Now, replacement policy. Now, the question is which block to be replaced on a cache miss? As I said, if the cache is directly mapped, there is no selection. There's only one block at each index, and this is the block that to be replaced. However, if we have a set associative cache and we have M is the number of blocks per set, then in this case, we have choices. We can have random replacement, select any block to be replaced. So we can, that will be very easy to implement in the hardware. Okay, so any block can be replaced inside the cache. So we call it random replacement. So how do we implement random? We can just use a counter. Now the counter is going to count from 0 to m-1. Yani for example, if we have, let us say, 4 blocks within a set, then we need a 2-bit counter, 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. So cycle by cycle, as the CPU is running, the counter is running, okay? And once we get a cache miss, we don't know when the cache miss will happen. Look at the value of this counter. Okay, look at the value of this counter and use it actually to select one of the 4 blocks inside the set. Okay, and that's basically how we can do it. This is called random replacement. And we only need one counter for the entire cache, regardless of how many sets we have. It does not really matter where we have the cache miss at what index. It's the same counter which is used for random replacement. That's one way. It's not really, maybe it's not really an intelligent way, but we can actually just replace any block. Okay. Now another way is called first in, first out, or FIFO replacement, which means that rather than having one counter for the entire cache, we can use one counter per set. Okay, again, it's going to count from 0 to m-1, but we change the counter every time we have a cache miss. Okay, so each counter, it will have actually to have, let us say if we have m equal to 4, it's going to count from 0 to 3. So this can be done with a 2-bit counter. So we need to store here 2 bits in each set for replacement to indicate that which block should be replaced next. So this is called first in, first out. So first we replace block 0, then 1, then 2, then 3. Then we go back to 0 and so on. And each set, okay, the blocks within each set are going to be replaced as first in, first out. It's called round robin. Round robin. That's also the meaning of first in, first out. First out. Now we increment the counter on every cache miss. So after replacing, we increment the counter so that next time we replace the next block and so on. So the oldest block inside each set is replaced. That's the meaning of FIFO. And finally, we have LRU, least recently used. Now, LRU is used actually in many caches today. Okay, for example, Intel has used LRU in its caches for years. And it's smarter than FIFO. Now, the problem with FIFO is that you might actually replace a block, even though it's the oldest block, but it's still actually being accessed. So it might not be the smartest choice to replace a block. So LRU is smarter than FIFO in the sense that it is tried to replace the block which is the least recently used within the set. So it's trying to guess which block is the least recently used and replace it. That's basically it. That's the meaning of LRU. So replace the block which is unused, okay, for the longest time. So how does it actually keep track of the block which is unused? Well, the way it is done is that every time you access a block inside the set, it becomes the most recently used. Okay? And therefore, you start actually stacking them from the most recently used to the least recently used. And then when you get a cache miss, look at the one which is the least recently used and replace it. That's really is how you do it. Now, I will tell you how to do this. If, for example, if m is equal to 2, if you only have 2 blocks inside, okay, each set, if you only have 2 blocks, then LRU is very simple. All what you need is just a single bit. Now, this single bit, every time you access, let us say, block 0, then block 0 becomes the most recently used, and block 1 will be the least recently used. So to indicate the LRU bit, if you access 0, then 1 is the the LRU bit. And if you access 1, then 0 is the LRU. It is just a single bit, but that's if m is equal to 2. Now, if m is equal to 4 blocks, then you need actually more bits, and it becomes slightly more complex to implement. Okay, so this is for this reason, you have to change, okay, these LRU bits, okay, every time you access blocks inside the cache. So LRU has the difficulty, it becomes actually costly to implement when m is large. And if you have a large number of blocks within each set, it becomes actually more costly to implement. So for this reason, people use some kind of an LRU approximation. Now, if the cache is large, if you have actually very large caches, sometimes random replacement, people have done a lot of simulations, okay, on caches to find which one is the best replacement algorithm. And basically, if you have your cache is very large, then it does not really matter. You can use random replacement. Sometimes it's as effective as LRU.